believe they'll be discussing large-scale adversarial swarm engagements. And gentlemen, the floor is yours.
Thank you, Colin. All right, I've shared my screen, so hopefully everybody sees it. I'm not going to repeat the title since Colin already said it. I would like to thank ONR and Cruiser Consortium here at NPS for supporting this work. Abe was going to join me in doing this presentation, and this has been done in collaboration with Claire Walton, who is now at UT San Antonio, Wei Kane, Theo Tsatsafanis, who is now back in Greece, and Chi Kong, who is at the University of Santa Cruz. Okay, we are interested in studying the following problems. So what we call an HVU, which is a high-value unit, we'd like to protect it from a swarm attack. This has been in the news lately, and this workshop has actually been addressing a lot of the related issues. And so the swarm has a large number of agents, and the objectives of our work are to determine what is a suitable framework for modeling these kind of swarm and swarm engagements in the following sense. We would like to understand, can we analyze the swarm engagements to determine what is success? And also, since these analysis tools can lead us to synthesis tools that will actually help us determine what are the best, what is, for example, the minimum number of defenders that we should employ for this particular mission, as well as what should be their trajectories that they should follow. The outline of the talk, first I will discuss how we construct with the framework. We show, in fact, that can be formulated as an optimal control problem. We discuss numerical methods to solve it. Then we go on to talk about how we can scale these problems to very large swarms on the order of thousands, and something that we have discovered in this process, which is the gap between the data-driven performance metrics, as you will see, and the model-based swarm defender dynamics, which is, in other words, the physical world and the world that tells us how we evaluate the metrics of performance. Using these tools, we actually have come up with some trade-off examples, and the talk will end with conclusions. So the main problem is we want to maximize survival of the HVU. Clearly, we need some way to model the performance of this engagement. And we're going to rely on so-called mutual attrition rate functions that I will discuss in more detail shortly. We need, of course, the swarm dynamics and the defender dynamics. So let me start with the performance criterion. It turns out that there's a large field, community that's been studying these kind of problems. It's operations research community. So operations research community since the 40s, since World War II, starting with the work of Koopman, has been using what they call instantaneous rate of detection functions. This is the way to try to determine, for example, trying to find something, and I want to find out how effective is my sensor. I can assign something called a detection rate function that here, for example, takes place of a Poisson scan model. In other words, if the subject I'm looking for is in the middle on XY plane, then probability of finding it is 1. And obviously it tails off as it moves away from that optimal spot. So these ideas of detection rate function have been extended in our literature to Lancaster attrition model, for example, clearly the optimal search. They can also be used to model the damage rates and to model probability of survival. There's been a lot of work done, obviously by Koopman, by Stone, by Washburn here at NPS, and we have published a paper in Naval Research Logistics in 2018 on this area. So what do these attrition rate functions look like? So the engagement we're going to study here, we have defenders, attackers, and the HVU. So the defenders are going to try to apply attrition rate to the attackers. Attackers are going to apply attrition rate to defenders, and of course, attackers are trying to destroy the HVU. So these functions are represented here. For example, the donut function could be something like a Gatling gun. So anywhere where it's red, it's probably likely that if you're there, you're going to be destroyed, or a standard limited field of view weapon, where the red implies that, again, if you're in that spot, your probability of being destroyed is very high. So what can we do with these pictures? Let me add a bit of mathematics here. And using this notation, let's say Q being the probability of survival of the attacker, PKD, same for the defender, and P, simply P for the HVU. And using this diagram that explains how the attrition rates work between each other, we can write down the following equation. Probability of survival of the attacker at time t plus delta t is going to be a function, obviously, of its probability of survival at time t times this product. In other words, this is the attrition applied at the attacker by every defender. And this is where this attrition rate function shows up, multiplied by the probability of survival of the defender at time t. So this is probability that the attacker will survive this interval delta t. So if I differentiate this equation, if I take a limiting operation, I will obtain a differential equation that looks like this, where you can see there's coupling between the attacker and defender probabilities of survival. And following the same steps, I can derive probability of survival of the defender at every time t. And these quantities, in fact, you will see are actually really important to understanding the engagements that we're trying to study in this talk. And finally, I can compute probability of survival of the HVU, which is, of course, conditioned on the probability of survival of the attackers at every time t. And using this latter quantity, I can define the cost function, since I want to maximize probability of survival of the HVU at time TF, where TF represents the time of the total time of the engagement. I want to minimize this cost function J. Now, on the side of the next step is the swarm dynamics. So we've considered two cases. One is what we call kamikaze swarm, in other words, where the attacking swarm trajectories are pre-computed. And in this case, the attackers, they do fire at the defenders, but they do not try to avoid them. So this is why we call them kamikaze. So they ignore the defenders and they exclusively trying to destroy the HVU. So in this case, the problem formulation looks as follows. This is the cost, minimizing probability of destruction of the HVU, subject to defender dynamics. In this case, they're just double integrators, and the equations that describe probabilities of survival of the attackers, defenders, and of the HVU. So this is essentially a standard optimal control problem. However, the cost is very different from the kind of cost that, at least I in my career have studied before, like LQR type cost, energy, minimum time, minimum distance, power, etc. So this cost comes from the OR field. So we were able to integrate this into our approach. What our people don't usually worry about are dynamics. And this is the stuff that we bring to the table, is combining both the OR-based approach to modeling these kind of engagements and the physical systems that actually participate in them. So on the active side, in other words, the next scenario is where the swarm is actively trying to avoid the defenders to get to the HVU. So we've actually looked at several potential base models. The one that we're going to present the results for here is based on the work by Naomi Leonard, but we also looked at Reynolds model, which is the oldest swarming model, I guess. We also looked at model by Ara Schwartz and pursuit evasion models used in, for example, biological literature. So this is the standard, this is the equation representing the swarming algorithm developed by Naomi Leonard, except that we've added an extra term. So first of all, the standard thing is that each agent gets attracted to its neighbors if they're in the range between D0 and T1. He repulses the neighbors when they're below D0, and he ignores them outside of D1. We have added a similar term to describe, to force the attackers, assuming that they know that where the defenders are, to avoid the defenders. And the virtual leader, which is the key feature of the swarming algorithm, in this case simply points at the HVU. And there's also a damping term. So with this, in this case, the problem formulation now changes a bit, and we have explicitly attacker dynamics here, which are coupled to the defender dynamics. And of course, the equations describing the probabilities of survival, attackers, defenders, and of the HVU. So this is standard optimal control problem. And to solve it, of course, there's been a lot of methods around. We have used the direct methods of optimal control. The idea is that you start with an optimal control problem, you discretize the time. And in this case, we also optimize simultaneously over the states and the controls. So this is different from a shooting method where you only optimize over the control inputs. So this gives us an nonlinear programming problem that we need to solve. And the idea would be we find these points, that's these optimization parameters, and then we interpolate between them. So this is the approach we used. the particular representation of the trajectories that we want to find, we use Bernstein polynomials. They were first invented by Sergei Bernstein when he was trying to come up with a constructive proof of Weierstrass theorem, but they're much better known as Bézier curves, and they're used in Acrobat to do the PDF fonts, and of course Bézier and de Casteljan have used them to pretty much start the computer-aided design field. Why do we like the Bézier polynomials? Is because they have a very nice feature, which is these control coefficients, which are the control points, which are the coefficients of Bézier polynomial. The curve generated by the Bézier polynomial is contained in the convex hull generated by the control points of the Bézier polynomial. So this allows us to do, for example, very easily find minimum distances between two Bézier curves, and also introduce the collision avoidance constraints in the optimization problem. So using Bézier polynomials, the discretization that we do, reducing to NLP, we have uniform discretization of the time interval. We approximate states and inputs using the Bézier polynomials. Differentiation, of course, again, using properties of Bézier polynomials, and integration is a simple Euler integration. With this discretization, we have been able to show that, in fact, if the optimal control problem has a solution, then for sufficient large order n, so does the NLP. And moreover, if I ask the following question, suppose I fix n and I solve my NLP problem, I get the control point coefficients that are optimal for that NLP problem. From those, I construct my controls and states, my states and controls, my apologies. Then the question is, if I let n go to infinity, and if that sequence converges to something, let's call it x infinity of t or u infinity of t, is that actually the solution to the original optimal control problem? And the answer is yes. And this work is actually follows in the footsteps of giants. The initial work was on the consistency of results, was presented in Pollack in his book from '97. There's been a lot of work done in this area by my colleague Mike Ross and his friends, and also by Rao. This result is actually published in Transactions on automatic control of last year. So to give an example what these engagements look like, in a kamikaze case, this is an HVU moving in the middle. We only have two defenders. They have very powerful weapons. The attackers are coming from both directions. And you can see the attacker trajectories are color-coded. As they get lighter, the probability of survival decreases. And in this case, this is a very successful engagement, simply because essentially the attackers ignore the defenders trying to get to the HVU. On the other hand, in an active engagement, a student, Theo, wanted to ask a question. What is the result if I have a swarm, in this case of 100 attackers versus 25 defenders? Defenders have much stronger weapons. What happens if I have the stationary position defenders, and you can see the attackers change color as they're being destroyed? Can I defend the HVU? And the answer is no. At some point, the HVU turns black, which means this was unsuccessful. On the other hand, if I do optimization for the same scenario, you can see clearly that the attackers are trying to avoid the HVU, but because defenders have more powerful weapons, they do destroy them. There is some bit of optimism in this result, and that's what Abe is going to discuss next.
So I'm unmuted now. I sound terrible. Apologies. There's a cold going through my house. So anyway, so thank you, Isaac. So this video is, you can go ahead and let it play. So I'm new to this field. This video is from my background, which is on soft matter physics. And so this is a simulation we wrote where we did an impact into 10,000 grains, right? So what you're doing in this simulation is you're solving the dynamics of every grain based on the position of its neighbors, right? And they exert forces on each other based on their relative position. So a classic molecular dynamics scheme, which is what underlies a lot of these agent-based swarm simulations, right? And so a question I had when I found Isaac, it was like, hey, we should do some work together, is can we scale up and study larger swarms? Like, how would that work? And so we had a lot of success doing that because essentially, well, the tools that go into both approaches, doing soft matter physics and doing swarm simulations are solving large numbers of coupled ordinary differential equations, which is what basically we've been telling you about so far. And so those could be the dynamics, or they're also now including for these swarm simulations, the attrition rates and the probabilities of survival. So go to the next slide. So something we did this. So we basically said, well, yeah, we can make our simulations better, and we can study very large systems. So here's sort of a toy simulation with where you can see the swarm starts as a big pink cube over there. It's gonna, after we click play here, yeah, go ahead, turns into a ball kind of slowly, and it's going to attack the HVU. And this is a particular example. So I could go through the whole historical progression of this, but I'm trying to give you the punchline here. Of an issue that we discovered. We said, well, this is a situation where we should be getting killed. Our defenders should be getting totally destroyed. And yet our optimizer has figured out, based on the faulty simulation test bed that we gave it, to make this sort of repulsive blob where all the defenders gather around and exert big repulsive forces on the attacking swarm and just keep it at some distance, right? So you say, well, obviously this is unphysical. So we called this ghost herding. So we said, okay, yeah, this is like a particular problem in the swarm on swarm simulations because we have ghost defenders who are herding the attacking swarm away. And you can sort of see how this plays out, right? If you look at the curves on these plots on the right in this particular engagement, all the defenders die, that's the blue curve. Mostly the attackers live, that's the red curve. And yet the HVU does not die, that's the green curve, right? So it survives even though it has no business surviving, right? So then an open question to us was, well, okay, this is a problem, a solvable problem, as I'll show you, but this is a problem for this particular kind of simulation that we want to study. Is this a broader problem for other similar types of simulations? Like, is this applicable to a broad class of situations for autonomy? And I think the answer to that is yes, and I'll try to explain why in a minute. Okay, keep going, guys. Next slide. Yeah, so mathematically, again, what we need to do is we need to couple whether the agents are alive or dead to the dynamics, right? I already essentially explained this, but we have these survival probabilities, and just sort of blindly applying the operations research tools with the dynamics, which many of you are familiar with, does not give, at least in some situations, results that are physical, because the dynamics need to know whether you're alive or dead, right? And so we can also do Monte Carlo simulations where we're actually randomly plucking agents out to test any kind of coupling strategies that we use to make these simulations more realistic. So you can go to the next slide. So, Monte Carlo simulations, I think probably everybody knows, sort of has a good idea what I mean when I say that, but basically we're studying the same kind of dynamics, but instead of continuously decreasing the survival probabilities, we just roll a random die at each time step, metaphorically, and decide whether the agent lives or dies based on its relative positions to everybody who's trying to attack it, and those attrition functions that we use as placeholders for weapon systems, et cetera, right? And so then, instead of the dynamics you're seeing here, you go to the next little bit here. Now, instead, the dynamics of the attackers are not just purely decoupled from those survival probabilities. We're using these Monte Carlo survival probabilities. So they're either ones or zeros, they're not continuously decreasing. And then the interactions are simply weighted by a 1 or a 0 with every other pairwise interaction in the system, right? So that way, if a guy dies, he no longer interacts with anyone else. And so then you can play the movie. So now you get a simulation that is much more, physically realistic. So you can see that the blue defenders are just being plucked out of the air and they're dying. And then the HVU dies, and you say, well, that's very sad, but yes, that's at least more physically realistic, and we won't have mission planners thinking that they're going to win when they will obviously not. Right? Okay, next slide. Okay, so you can't, well, you can, but it's extremely computationally intensive, and there are some actually sort of theoretical questions of how and under what conditions it's possible. But practically, it is very challenging to use these random simulations to do any kind of optimization, right? Because, well, you have randomness. And so we wanted to show at least proof of principle that you could couple the attrition and the dynamics in a simple way in order to make things smooth still, that a gradient based or some other kind of optimization scheme could easily or straightforwardly find the best solution. And so we did that with two ways. The details are not crucial, but I mean, they're sort of self-explanatory in their titles. So essentially, we weighted pairwise interactions by probability of survival, but now instead of binary, it's continuously decreasing, right? So you can see that xi double dot, that formula is the dynamics of the attackers on the left. And so, thank you, Isaac. Yeah, so qi or qj and pk are the survival probability. So it's basically saying, okay, if you're 50% alive, then you only interact 50% with pairwise forces. You say, well, that's also physically a gross approximation. The second approach is just a damage type model. So basically, when you get to 50% chance of being dead, we pluck you out, not randomly like with Monte Carlo, but in a continuous way, a way that's predictable and does have a discontinuity, but is still not random, right? So we can optimize on either of these two, but more importantly, we can just run an engagement where we say, does this give the same results that Monte Carlo does? And indeed it does, right? So you can see the plots on the right show that all the Monte Carlo and then these two sort of very simple ways that we've coupled attrition with dynamics more or less give all the same results, right? The defenders and HVU die at about the same cut time, and the predicted number of remaining attackers are about the same. So these work pretty well if you wanted to use this for the scheme that we're sort of proposing here. Okay, next slide. So then just to drive this point home, I mean, this is essentially more of the same. I won't dwell on this, but this is essentially like how many defenders do you need to accomplish the mission? And you can see that you're going to need more than 50 just by logic, because you know that the HVU, well, that the attacking swarm has 50 and that they have slightly better weapons than you do. So you say, okay, I'm going to need more than 50, I think. And so you can see that these two heuristic models that we came up with both essentially predict that. That's when the HVU destruction probability drops from 1 to 0, is around 52 for one and around 65 for the other, say. Whereas this uncoupled model, this ghost herding quote model, says, yeah, you can win the engagement with only 20 defenders, which is obviously unphysical, right? And so that's a hallmark, as I'll sort of say in the next slide, of if you have, so you imagine that you run an engagement with our simulations at say 35 defenders, you're going to get a wildly diverging set of performance metrics out, depending on whether you are properly coupling attrition with the dynamics of your simulation going forward. Okay, next slide. Oh, so superfluous arrow. Okay, so just to sum up, we wanted to cast a swarm-on-swarm engagement in terms of a tractable optimal control problem, tractable. So we combined two simulation schemes that are commonly used, one from the operations research community, from Koopman, Lancaster, and others, on sort of smooth attrition or smooth search functions, and then also with the sort of well-known, at least by this community, swarm dynamics algorithms to create a simulation environment where we could do this. This does work well, especially in kamikaze scenarios, but we found that in the active scenario where the defenders could respond to the attackers and vice versa, that we needed to couple these two better than we were in the initial simulation. And we believe this is like essentially an inherent issue in any adversarial autonomy modeling situation, so that the adversarial nature doesn't have to be weapon systems. It could be terrain or weather. If you have a group of robots trying to accomplish some task, and you say, okay, depending on where they are, they have some spatial function that says, yes, if they're over there, that's more dangerous. I'm more likely to get struck by lightning at the top of the hill or eaten by the Loch Ness monster when I go close to the lake or whatever. And then what the rest of the swarm does to accomplish whatever its mission is, it does depend on whether or not that guy was plucked away, right? So they're going to have to sort of cover his region of the search that they're trying to do, or whatever it is, right? So we're working on essentially showing right now how this can be applied to optimal search problems and some other some other similar problems besides just this, right? And we also showed sort of there at the end about how you can recouple these in simple ways, and there's good promise that using heuristic coupling between attrition and dynamics can give good results going forward. So I'll stop there, and we'll be happy to take any questions.
Thank you very much. Great talk, gentlemen. I think we have time for, yeah, we're getting some claps there. We have time for a couple of questions. I have some curiosity ones if nobody has any. Go ahead, George.
Yes, thank you, Isaac and Abe. Have you considered the case where, let's say, the interaction, the adversary action is not, let's say, kinetic, and so the agents don't get taken out permanently, but they get taken out temporarily, let's say, by some other type of action? I mean, maybe they're communicating and there's somebody that takes away their communication capabilities for temporarily and so forth. How would that play in this kind of game? I mean, have you considered that case?
Well, we haven't yet, but it's a function of modeling. So in this particular case, we model the scenario where probability of survival is explicitly bound to the fact where the agent lives or dies. But in your case, we would have to simply expand the model to include the situation you just described.
Okay,
So
but it's possible, and
it's absolutely possible.
Yeah, okay.
You just have to, I don't know if you want to use attrition rate functions, if you want to use some other formalism. The key is that, in general, you have to come up with a formalism that will model this idea that the agent is out for some other reason and therefore cannot contribute to the mission. So if there is a way to mathematically represent it, we should be able to handle it, yes.
Okay, thanks.
Any other questions? So for the attrition rate functions, I mean, I know that those were kind of, you had the Gatling one, which was the donut, and then you have the limited field of view. Those are kind of arbitrary selections, I'm assuming, right? Like just to get that attrition rate function in there. Do you actually have attrition rate functions for actual weaponry? I mean, those things are available.
The standard answer. If I tell you, I'd have to kill you.
Yeah. Increase my attrition probability.
No, but
so
if you look at OR literature, essentially, they do the same thing, right? They have some generic functions that represent attrition rates. And these are just examples of those functions.
Right.
So if you want a specific weapon function, then clearly you would have to go, go to a different environment and talk to in a very different level. Regarding yes. like weapon specifics.
Certainly. So then,
but generically, weapons effectiveness is represented using some variation of what we've shown.
Okay. So okay. So then
and another wrinkle.
Yep.
Another wrinkle is that the models we use target everybody at once, right? So there's certain kinds of weapons that could do that, but like a conventional gun, you say, well, yeah, that would be a future direction, is like to basically compare targeting one agent at a time. So what we're doing right now that is sort of just a proof of concept, but yeah, there are many kind of unphysical wrinkles in the weapons models we're using.
Okay, so if I have in some of your swarm models, let's say I have a field of view scenario, then you talked about the range, but if I had two defenders that have overlapped field of fire on or attackers, then it's just the summation of those functions depending on where those agents live within those field on that function.
It's not summation, it's that long formula. Essentially, it's they're all assumed to be independent. It's that product.
Okay.
Yeah, you have to do the product that you survive every attack and then one minus that. Yeah.
So the fact that they intersect doesn't matter. It's just every attacker is firing at you, and so it's the product of being attacked by everybody in the opposing side.
And so for some of those, go ahead.
We have in that 2018 paper, we have addressed, for example, a discrete number of shots to destroy an agent. So it won't be just continuous fire. So actually you say, and some 10, and you're out. But and maybe that would, George's earlier question. So some of that modeling may help with the kind of things he was talking about, where the agent could be out because some equipment problems, right? Or he's doing something else. So this is a temporary thing. It could be construed as some. You'd have to have some sort of discrete way to represent the situation, some discrete math.
Okay, thank you. And then for the simulations that you were showing, a lot of those had the interesting videos there. Are those all under one type of attrition function in general, or did you try a bunch of different?
You're asking us what is technology readiness of our simulation? No, we haven't. What Abe was saying, right? We can change the fire. So the shape of the function was the same, but for example, when we change the range of the weapon or the firing rate, this could be different.
Right,
but the shape was the same.
Were you using the limited field of fire one, or did you have, what was your favorite function?
We just use the bell, like the
Okay.
The bell. The bell is the favorite.
Okay, gotcha.
It's the
All right, that's all I got. Is anyone have any other questions? Oh, thank you very much. That was a great talk.